So for Chapter 2, Lesson 2, we're going to look at atoms and ions and the periodic table and how it is arranged. Here are a list of the learning goals that we will learn in this section, ranging from Dalton's atomic theory all the way down to the arrangement of the periodic table and where the metals, nonmetals, and metalloids are. Also, we'll talk about isotopes. If you'd like to pause and read through those goals, feel free to do so. Here is a list of the new vocabulary terms that we will learn. Off to the left-hand side, continuing on to the right. You'll also notice that there is an equation that we will learn as well. And this will be for isotopes when we're trying to figure out the atomic weight using the abundance of the isotopes. So looking at Dalton's atomic theory. Dalton's atomic theory is made up of 4 postulates. The first postulate says that matter is made up of atoms. So if you remember the definition of matter, matter is anything that has mass and occupies space. So postulate 1 is saying that matter, anything that has mass and occupies space, is made up of atoms, which makes sense, right? We're made up of atoms. The air that we breathe is made up of atoms. The computer in front of us is made up of atoms. The headphones, if you're wearing them, are made up of atoms. And not only this, but those atoms that make up matter are indivisible and indestructible. Okay, so atoms are very hard to destruct. We have been able to split atoms with new technology, but that does not apply to Dalton's atomic theory. Now looking at postulate number 2. All atoms of an element are identical. So when you're looking at the periodic table, which is made up of elements, and you pick an element off the periodic table, so say you pick oxygen. What postulate 2 is saying is that all atoms of oxygen are identical, just like all atoms of hydrogen are going to be identical. Postulate 3 now is saying atoms of different elements have different weights and different chemical properties. So all that means is if you're comparing two, so if you're comparing the element of hydrogen and the element of oxygen, hydrogen atoms are going to have a different weight and a different mass than oxygen atoms. Similarly, hydrogen atoms are going to have different chemical properties than oxygen atoms. Now looking at postulate 4. Atoms of different elements combine in simple whole number ratios to form compounds. So we actually talked about this in chapter 1 when we looked at pure substances. And one of the pure substances could be either an element or it could be a compound. So postulate 4 is just saying that when compounds are formed from 2 or more different elements or atoms, that they always form with whole atoms. So you never take half an atom to form a compound. It's always whole number atoms to form compounds. The law of conservation of mass states that mass cannot be created or destroyed. So looking at the picture below, in the example, we have the reactants in an Erlenmeyer flask in the first part of the picture. So it looks like we have silver 1 nitrate and sodium chloride together in a closed system. So by closed system, all I mean by that is that it does indeed have a cork on it so that we're not losing any material to the outside environment. So when we put the reactants into the flask, the mass of those reactants is going to equal the mass of the products. Why is the mass of the reactants going to equal the mass of the products? It's due to the law of conservation of mass. It's saying mass cannot be created or destroyed. It's just rearranged. So when we do a reaction with the silver nitrate and sodium chloride in this case, those atoms might be rearranged to form new compounds, but we're not losing any mass in the process, especially if we have a closed system. Now, although theoretically we don't lose any mass, when you get into labs and you start doing actual calculations on your own, you'll notice that you will be losing mass. And when you lose the mass, you're losing it due to transitions, due to residue being left on an Erlenmeyer flask or a different piece of equipment that you used. Next, let's look at the law of proportions, also known as Proust's law. The law of proportion states that any chemical compound will always contain a fixed ratio of elements by mass. So what exactly does that mean? It means the atoms that make up a compound are going to be the same mass ratio. If the ratio changes, then so does the compound. So let's look at the example here. So in the top example, we have one carbon atom and one oxygen atom combining. So that's the ratio, a 1-to-1 ratio. So when we combine one carbon atom with one oxygen atom, we get a 1-to-1 ratio of carbon and oxygen to make carbon monoxide. Now, if we were to change the ratio to a 1-to-2 ratio, so reacting one carbon atom now with two oxygen atoms, it would result in a 1-to-2 ratio of carbon to oxygen, making a different compound, carbon dioxide. So since we changed the ratio, as it says at the very bottom of the slide, if the ratio changes, so does the compound. Because in the first example, we have carbon monoxide, a 1-to-1 ratio of carbon and oxygen, and in the second, we have carbon dioxide, a different compound with a 1-to-2 ratio. Next, we're going to look at the composition of an atom. So in the picture off to the right, we have a pictorial drawing of an atom, a representation. We also have a table with all of the subatomic particles and their properties. So let's look at the table first. Looking at the subatomic particles that are present in an atom, there are 3 subatomic particles present. There are protons, neutrons, and electrons. So what do you need to know about protons, neutrons, and electrons? You need to know their charge, their atomic mass, or approximate atomic mass, and also their location within an atom. So let's look at protons first. So protons have a positive charge. They are represented by the red spheres in the picture off to the right. For the mass of protons, their atomic mass units is approximately 1. And they are located, as you can see from the picture, in the center of the atom, which we call the nucleus. The next subatomic particle we'll look at is the neutron. A neutron's charge is 0, which makes sense, right? Neutron, think neutral. That'll help you remember that its charge is 0. Much like the charge for a proton is positive, so P for positive, proton. N for neutral, neutron. Now the mass of a neutron is also 1, similar to proton. It is also located in the center of an atom, which we call the nucleus, and you can see it represented off to the right with the green spheres. Last but not least, the electron is the last subatomic particle present in an atom. The charge on an electron is negative, so an electron has a negative charge represented by this minus sign here under the charge center. Now for the mass of an electron, they do have a mass, even though in this table it has a number 0. But its mass is so small that it's negligible, so we just round it to 0, count it as 0. Now, the electron is the only one of the 3 subatomic particles that are not present in the nucleus. And you can see these yellow spheres that are surrounding the nucleus. So the electrons actually orbit the nucleus. And why do they orbit the nucleus? Well, if you think about the charges, we have the nucleus in the center, which is this center pocket that contains all of the protons and neutrons. And now notice the nucleus, since it has positively charged protons and neutrally charged neutrons, so the overall charge of that center nucleus is going to be positive. So we have a positive center. Now we know that opposites attract, and electrons are negative, so they're opposite charge of that positively charged nucleus. So they're attracted to that positively charged nucleus. So that is what causes them to orbit around that positive center because of that opposite attraction. Now, how are we going to use this information in class? Well, first off, you're going to need to be able to identify what the atomic mass or the mass number of an atom is. And you can do that simply by adding the number of protons plus the number of neutrons. So if you look at the diagram of an atom, to figure out the atomic mass of that specific atom, all you would need to do is count the total protons and neutrons. So if I look at this atom, I can see that there are 4 green neutrons and 3 red protons. So that must mean that the atomic mass of this particular atom is going to be 7. 3 protons plus 4 neutrons gives me 7. What else you can figure out just by using the atomic composition of an atom is the charge of an atom. Now, when you're looking at charge of an atom, you ignore neutrons because neutrons don't have a charge. So you only focus on the protons and the electrons. Now, in the case of this particular atom, there are 3 positive protons located in the nucleus and 3 negative electrons surrounding the nucleus. So, since we have 3 protons and 3 electrons, and remember the electrons are negative, the total charge of the atom is going to be 0. So anytime the protons and electrons are equal to each other, the charge of the atom is going to be 0 or neutral. Let's look at some examples of atoms and introduce the concept of an ion. Now, in the first example, we have a lithium atom, which is the same atom that we had on the previous slide, but let's do the count and see how we would work through this problem. So looking at the picture of a lithium atom, to figure out how many protons there are, we look at the positively charged red spheres that are located in the nucleus, and it looks like there are 3 of them. The electrons then are going to be the 3 negatively charged spheres that are surrounding the nucleus or orbiting the nucleus. Now this makes sense when you look at the lithium atom because the lithium atom is neutral, and neutral atoms always have the protons and electrons canceling each other out. So there should be the same number of protons and electrons in a neutral atom. For the neutrons are the green spheres located in the nucleus of an atom. Now remember, neutrons are neutrally charged, so they don't have a charge. So looking at the overall count, we have 3 protons, 3 electrons, and 4 neutrons. Now let's go down to the bottom example with fluorine. So this is a neutral fluorine atom. So since it's a neutral fluorine, meaning it doesn't have a charge, that means the protons and electrons should equal each other. So go ahead and count them and see if they do. Now when I look at the protons, I see 9 positively charged protons in the nucleus of the fluorine atom. That means there should also be 9 yellow negatively charged electrons orbiting that nucleus in order for it to be neutral. Now for the neutrons, it looks like we have 10 is what I count. So there's the overall count for a neutral fluorine atom represented on this drawing. Now let's look at the definition of ions. So we're going to start with a lithium ion. So looking at the top one here. So a lithium ion, what exactly is an ion first of all? An ion is an atom that has a charge. And the reason that atoms have charges is because their protons and electrons do not equal each other. So they either have more protons or they have more electrons. Now we have 2 different categories of ions. The first category is called a cation. So a cation is a positively charged ion. And positively charged ions only occur when the protons are greater than the electrons. Now, an easy way to remember that a cation is a positively charged ion is simply looking at the word itself. So cation can stand for I see a, and then the T becomes a plus sign, so C a positive ion. So that's how you can remember that cations are the positive ions. Now, how is a cation formed? Well, a cation is actually formed by the loss of an electron. Now, why is it formed by a loss of an electron instead of by the addition of a proton? Well, protons do not change within an element. So what I mean by that is lithium, we said, has 3 protons, right? All lithium atoms will have 3 protons all the time. The protons of an atom do not change. If you change the number of protons in an atom, you are changing the identity of that atom. So if I were to change the protons of lithium from 3 to 4, it is no longer lithium. It is now a new element. So if you change the protons, you're changing the identity of the atom. That's why it's the electrons that change when we form ions, because you can change electrons without changing the identity of an atom. So in this case, with the lithium ion, it still has 3 protons, whether it is neutral lithium or whether it is the lithium ion. The difference is the electrons. So in neutral lithium, the electrons were equal to 3. So when we go over here to the lithium ion, you'll notice there are only 2 electrons for a lithium ion. So 3 protons still, because it's still lithium, but the electrons are now less. There's only 2 yellow spheres in the picture. So since the protons and electrons no longer equal each other, we now have an ion, and in this case, a +1 ion, because protons are positively charged. So there is 1 more positive than there is negative, so that's how we get the +1. Let's look next at an anion. So we said cations were positively charged ions, so you can guess that anions are negatively charged ions. So since protons can't change, that means that the electrons are going to change. So in this case, in the case of anions, electrons are added to the atom so that there are more electrons than there are protons. Since electrons are negatively charged, this is going to give a negatively charged ion. So in the case of fluorine, the electrons went up to 10 and the protons remain the same. Next, we're going to look at atomic symbols. Now, atomic symbols are different than how elements are represented on the periodic table. Atomic symbols are a way that we represent different isotopes, and we'll cover isotopes later in the chapter. For now, we're just going to look at the properties and aspects of the atomic symbol itself. We're going to start with the atomic number, which is represented by the letter Z in the lower left-hand side of the atomic symbol. So what is the atomic number? Well, the atomic number is equal to the number of protons of that particular atom. Now remember, when we're talking about the number of protons of an atom, that defines the identity of the atom itself. So the number of protons do not change for a given element. For example, if I was talking about oxygen, the element oxygen, all oxygen atoms are going to have 8 protons, no matter what. If you change the number of protons, you are then changing the identity of that atom, and it will no longer be an oxygen atom. So, since all oxygen atoms have 8 protons, that means the atomic number for oxygen is going to be 8. Next, let's look at the mass number, represented by the letter A in the upper left-hand corner of this atomic symbol. So for mass number, we've actually already talked about mass number. Mass number is going to be the protons and neutrons located in the nucleus of that particular atom. Because remember, protons and neutrons are the only 2 subatomic particles that have mass. So if we can add the number of protons and neutrons together, we can figure out what the mass number is. With atomic symbols as well, you'll notice that the mass number is always going to be a whole number, since protons have an atomic mass unit of 1 and neutrons have an approximate mass unit of 1 as well. Now, what is this letter X? This letter X is the element itself, and you can find that representation of that element on the periodic table. How are we going to be using these atomic symbols? Well, we can actually use them to calculate any of the subatomic particles. So in the example below, we're going to look at two different atomic symbols, and we're just using those symbols, we're going to calculate the number of protons, the number of neutrons, and the number of electrons. So the protons is the easiest part to figure out. Looking at this atomic symbol of fluorine, if you remember, the number of protons is the same as the atomic number, and the atomic number is the number located on the bottom left side of the symbol. So in this case, it is going to be the number 9. So that means the number of protons is 9. Now, oftentimes, when they're representing atomic symbols, they leave out the atomic number. Now, why would they leave out the atomic number? The reason is because you can figure out what the atomic number is simply by looking at the periodic table. So if you find fluorine on the periodic table, fluorine is number 9 on the periodic table, meaning its atomic number is 9. Since its atomic number is 9, that means it has 9 protons. So they can omit that number since protons do not change for a given element. Now for the electrons, that's going to be the next easiest one to figure out, because you'll notice this atomic symbol is neutral. How do I know that it's neutral? Because if there is a charge on an atomic symbol, it is going to show up in the upper right-hand corner. So I'm making a little circle here to where the charge would be if there was one. So if you see a plus or a minus sign in the upper right corner of that atomic symbol, then it has a charge. If there's nothing there, that means it's neutral. So in the case of this fluorine atom, it is neutral. So since it's neutral, that means that the protons and electrons have to equal each other. So if there are 9 protons, that must mean that there should be 9 electrons as well. Now, last but not least, to figure out the neutrons. So we know what the mass number is because they give us the mass number in this upper left-hand corner. So the mass number of this particular fluorine atom is 19. And remember, mass number is the protons plus the neutrons. So if there are 9 protons and the mass number is 19, to figure out the number of neutrons, all we have to do is subtract those two. And it works out nice with these atomic symbols because you just take the mass number and subtract the number of protons, and it's all lined up perfectly for you. So 19 minus 9 gives me 10, meaning that in this fluorine atom, there are 10 neutrons. So let's go ahead and do the next one. We'll go a little bit quicker through this one. So lithium, how many protons are there in lithium? Well, there are just 3. You can see that by the atomic number represented here. If that number is missing, then you just go to the periodic table, find lithium on the periodic table, and you'll see that lithium is number 3, meaning it has 3 protons. Now for electrons, this atom is also neutral since there is an absence of a charge. So that means the protons and electrons equal each other, so there are also 3 electrons. To figure out the neutrons, you take the mass number, which is 7, subtract the number of protons, which we decided was 3, and what's left over is going to be the neutrons, because protons and neutrons are the only 2 subatomic particles that contribute to mass. So in this case, we have 4 neutrons. So next we're going to look at isotopes. On the previous slide, we looked at atomic symbols, which I said are representations of isotopes. So what exactly is an isotope? An isotope are atoms of the same element that have a different number of neutrons. So since they have a different number of neutrons, that means they're going to have different mass numbers. Now, having a different number of neutrons can affect the stability of an atom. So the example we're going to look at is carbon. So we have two isotopes of carbon represented here. In the top one, we have carbon 12. So I call it carbon 12 because its mass number is 12, as you can see by that number in the upper left-hand corner on the side of that atomic symbol. Now in the bottom isotope, it's also carbon, but notice the mass number is different. It's carbon 14. So since the mass numbers are different, that tells me that these two isotopes, these two atoms, have a different number of neutrons. How do I know that it's the neutrons that differ? Well, because the protons cannot change. As you can see, since they're both carbon atoms, they both have to have 6 protons. And you can confirm that by looking at a periodic table and seeing that carbon is number 6 on the periodic table. So if we were to change the number of protons, it would no longer be carbon. It would now be a different element. So these are two isotopes of each other, or two isotopes of carbon, because they have different mass numbers. And their mass numbers are different because of their number of neutrons. So let's look. How many neutrons does carbon 12 have? So to figure out the neutrons of carbon 12, we take the mass number and then subtract the number of protons. So the mass number is 12, the number of protons is 6, so we just subtract that and we get a total of 6 neutrons for carbon 12. Now in the bottom example, to figure out the neutrons, we do the same thing. We take the mass number and subtract the number of protons, so 14 minus 6. And that's going to give us 8. So for carbon 14, there are 8 neutrons. Now you see that they differ by the number of neutrons, but isotopes also differ because their stability is affected when the neutrons are changed. So carbon 12 is going to be a more stable carbon isotope, whereas carbon 14 is actually radioactive, and it's used to predict the age of organic artifacts, so it can have different uses. Now we're going to look at atomic weight. Now atomic weight is different than mass numbers. So far we've just looked at mass numbers, which are whole numbers representing the number of protons and neutrons present in our particular atom. Atomic weight is not a whole number. It is the number represented on the periodic table. So you can see a cutout of a chlorine element from the periodic table off to the right-hand side. Now you'll notice the mass number is 35.453, not a whole number. And the reason that it's not a whole number is because that atomic weight represented is an average of all of the isotopes of chlorine, their masses and their abundance. So how do we figure out the masses of the chlorine isotopes and the abundance of the chlorine isotopes? Well, we use what we call a mass spectrometer. And what a mass spectrometer does is it separates atoms based off of their mass. So if you put a sample of chlorine gas into a mass spectrometer, it is going to take all the atoms in that sample and it's going to separate them by mass, and it's going to count those atoms as they exit so that you know how many atoms had a mass of 35 and how many atoms had a mass of 37. So that's the results that we see over here off to the left. So the results say that 75.78% of all chlorine atoms exist with a mass number of 35. The remaining chlorine atoms, so 24.22%, exist with a mass number of 37. So we use these values in a calculation using the equation above to figure out the atomic weight that is present on the periodic table. You can see a sample calculation below. So to do this, we take the mass of 35, multiply it by the abundance, and notice the abundance is not in a percent. So we change it from a percent to a decimal, and if you don't know, in order to change a percent to a decimal, you just move the decimal place 2 times to the left. So that's how they got 0.7578. So this is representing the chlorine 35 isotope. You then take that and you add it to the chlorine 37 isotope multiplied by its abundance, which when in decimal form is 0.2422. Once you complete the calculations, we end up getting 35.48, which is close but not exact to the atomic weight represented on the periodic table. Let's do another example. Feel free to pause and try the example on your own to see if you're grasping the concept. So in this situation, we have an unknown element that has 2 naturally occurring isotopes, very similar to the previous example with chlorine. One of the isotopes has a mass of 62.930 and an abundance of 69.17%. The other isotope has a mass of 64.928 and an abundance of 30.83%. So we need to figure out what is the average atomic weight for the element. So we're going to use the equation on the previous slide to figure that out. Once we figure out the average atomic weight, we can then take that atomic weight and compare it to atomic weights on the periodic table and figure out the identity of the element itself, which is what question 2 is asking. So here's the work shown to do this. You can see that we take the first mass of 62.930 and we multiply it by the abundance. Now here they showed the percent divided by 100 to get it into decimal form. So you can either do this or you can simply move the decimal point over 2 to get 0.6917. Then they add that to the second isotope mass multiplied by its abundance to get an overall mass of 63.55 grams. You then look at the periodic table, at the masses on the periodic table, and find the element that is closest to 63.55. And when I'm looking here, I see that copper is the closest to that. So copper has a similar atomic weight, and its symbol is Cu. Let's look at the periodic table and how it is arranged. So the periodic table is actually separated into sections based off where the metals, nonmetals, and metalloids are. So looking at this periodic table in front of us, you can see by the key at the bottom that the metals are the ones in blue. So you can see we have all of the metals mainly on one side of the periodic table with the exception of hydrogen here. Now the metalloids are actually in green, and the metalloids are what separates the metals from the nonmetals, as you can see on the periodic table. So you might be able to see this bold zigzag line starting right at the edge of boron here. So everything touching that line except for aluminum is going to be a metalloid. So that will help you remember where the metalloids are. And that'll also help you remember where the metals and the nonmetals are, since this is the line that is separating the metals from the nonmetals. Last but not least, the nonmetals in yellow, as you can see from the key here. So they're all going to be on this side of the periodic table. Notice that hydrogen is an exception. It's hiding over here with the metals, and we'll talk about why that is later on in future lessons. So what do you need to know about metals, nonmetals, and metalloids? Well, looking at the asterisks here at the bottom of the slide, what you need to know about metals is that they are generally shiny solids, except for mercury. Mercury is a liquid at room temperature, but most other metals are solids. They are malleable, meaning they are flexible, movable. They can be shaped into different things, and they can conduct electricity. So, generally shiny solids at room temp, malleable, and can conduct electricity. Now, for the nonmetals, what do you need to know about nonmetals? The nonmetals are generally dull, brittle solids or gases. So they exist as both solids or gases. And that makes sense. If you look at the nonmetals, we got oxygen and hydrogen and helium, right? Those are all gases. But then when you get further down the periodic table and you get to iodine and bromine, those are going to be solids at room temperature, sulfur as well. And they do not conduct electricity. Okay, so that's the difference between the two. Metals can conduct, nonmetals cannot. So you not only need to know where the metals, metalloids, and nonmetals are on the periodic table, but you also need to know certain specific groups. And when I'm talking about a group, I'm talking vertically, up and down the periodic table. So going in this direction is a group. You do not need to know every group on the periodic table, just the ones that are labeled here. So let's start with the first group of alkali metals. So alkali metals are going to be group 1 or 1A here, depending upon how the periodic table you have is labeled. Now remember, hydrogen is just hanging out over here, but it's really a nonmetal. So hydrogen is not an alkali metal in this case. It's all the rest of them in group 1. So lithium, sodium, potassium, rubidium, cesium, francium. Those are alkali metals, and you're going to need to remember that name, okay? It's not going to be given to you on the periodic table. Group 2 now, 1 over, this is alkaline earth metals. So beryllium, magnesium, calcium, strontium, barium, radium, those are the alkaline earth metals. Now these two groups of metals are referred to as the main group metals. So alkali metals and alkaline earth metals are the main group metals. Now this big block in the center here is the transition metals. Okay, so when I say this big block in the center, I'm talking if you would draw a line here and then draw a line here. So this whole block is the transition metals. Now we do not have common names for group 13 or 3A, group 14, 4A, group 15, 5A, or group 16, 6A. So why don't we have common names for those ones? Well, if you look at those groups, you'll notice there's a mixture of metalloids, nonmetals, and metals in those groups. So the reason we have common names for the other groups is because they have common properties. For instance, the alkali metals and the alkaline earth metals will have common properties, common oxidation states, common reactivity, so on and so forth. So that's why we give them proper names. So we're skipping 13 through 16 and we're going to group 17 here, or 7A. So group 17 or 7A are referred to as the halogens. So fluorine, chlorine, bromine, and iodine are the halogens. The word halogen actually means salt former. So they like to form salts. For instance, chlorine, more specifically, you've probably seen every day forming a little salt called sodium chloride, the salt that we put to season our food with. Then the last name that you need to know is this last group, group 18 or 8A. This is the noble gases. So helium, neon, argon, krypton, xenon, radon. Okay, so those noble gases, what do they have in common? Well, their general property is that they're not very reactive. They're very stable. I mean, if you think about helium, for instance, helium is a gas that we use in balloons at children's parties, right? If it was very reactive, we wouldn't have it in a balloon at a kid's party near open flames. And by open flames, I'm talking about the candles on a birthday cake. So they all have similar properties as well. So what else can the periodic table tell us? It can tell us where metals, nonmetals, and metalloids are. It also gives us certain groups with similar properties and reactivities, but it can also help us predict ion charges. So we talked about ions previously, remember ions were charged atoms, so either a positive charge, cation, or a negative charge, anion. So the periodic table can actually help us predict what charge that particular atom will form. So will it lose electrons to form a positive charge, or will it gain electrons to form a negative charge? So off to the right here, we have a general trend. So you'll see that metals will tend to lose electrons. So if they're losing electrons, that means they're losing a negative charge. So if they lose a negative, they're going to become positive. And the term for a positive ion is a cation. So whenever you see a metal, as long as you know where the metals are, they're almost always going to form a cation, a positive charge. So they're going to like to lose electrons. Now nonmetals, remember these are the guys over in this side here, they like to gain electrons. So if they're gaining electrons, they're gaining a negative charge and they're going to form an anion. Now this makes sense because we'll actually see ionic compounds are almost always between metals and nonmetals. And that works out nice because metals like to lose electrons and the nonmetals like to take those electrons that the metals are losing. All right, now let's look at the charges. So in this first group here, group 1, remember, these are the alkali metals. Notice, with the exception of hydrogen, since hydrogen is not a metal, they like to form a +1 charge. So you can guarantee they will always form a +1 charge in this course. The alkaline earth metals, so the second main group metals, they like to form a +2 always in this course. They will be a +2 charge when they form an ion. Now the transition metals, those can be variable charges. So they don't always form one charge. So that's why those are just in blue with no charges associated. Now going here into group 13. So this is where boron and aluminum are. So these 2 +3 signs, this is boron and aluminum. So boron and aluminum like to form +3 charges in this course. Okay, now they skipped this group here because this group sometimes forms +4 and it sometimes forms -4. So it can have a variety. So that's why group 14 is blocked off in red here. Okay, now group 15, so we're looking at the row that starts, sorry, not row, column that starts with nitrogen, they like to form -3 charge. So notice we're getting into the negatives. Why? Because now we're hitting the nonmetals, and nonmetals like to form anions. So nitrogen and below, those ones like to form -3 charges. Now in group 16, we're going to see them forming -2 charges. This is the group that has oxygen in it. And oxygen always is going to form a -2 charge for us in this course. Last but not least, we have the halogens. So the halogens in group 17 here always form a -1 charge. So if you see chlorine or fluorine or bromine and it is forming an ion, it's always going to be a -1 charge on that ion. Last but not least, notice we have the noble gases, and those are a special case as well. They're not very reactive, so they don't often form ions of any sort. Right now we're going to look at the diatomic elements on the periodic table. So when I use the word diatomic, di meaning two, these are elements that can't exist by themselves in nature. So what I mean by that is hydrogen is one that likes to form diatomic element in nature. So hydrogen, just one hydrogen atom by itself, is not stable enough. So what it does is it finds another hydrogen atom and it pairs up with that other hydrogen atom so that they can stabilize each other. Okay, so there are 7 elements on the periodic table that form diatomic elements in nature, meaning they're not stable with one atom on their own, so they find another atom of the same element to pair up with. Now this is going to be very helpful to know in later chapters when we start talking about and predicting products in reactions. Because anytime you have any of these 7 elements as a product, it's always going to form a diatomic. So H2, O2, Br2, N2, Cl2, F2, I2. Okay, so they're always going to form diatomics. You're not going to see any of them, a single atom, by itself. Now, How do you identify where these are, or how do you remember these? Well, they form a 7 on the periodic table, which is nice since there are 7 of them that they form that number 7. Now notice hydrogen once again is being the exception. It's kind of a stinker hanging out over here by itself, but the rest of the 7 do form a 7 on the periodic table. So I'm going to draw that now. So starting at nitrogen here, moving over to oxygen, which also likes to form diatomics, and then you hit fluorine. Once you hit fluorine, then you continue down the halogen list all the way to iodine. So these are 1, 2, 3, 4, 5, 6 of the 7, and then the 7th one, of course, is hydrogen hanging out over here by its lonesome. So try to remember that those form diatomics in nature, especially when we get to predicting products. That will really help out. Now let's try a practice problem using what we just learned about the arrangement of the periodic table. So the situation says we are wanting to study one of the elements, strontium. You will need to remember important facts about the element to prepare ourselves. So if you have a periodic table at home, please get it out or try to pull one up so you can follow along and solve this problem with me. Using the periodic table, what will be the atomic symbol and the properties for the element of strontium? Okay, well, the atomic symbol itself, that is going to be, you'll have to find that on the periodic table along with the mass and the number of protons. That's what's going to be the atomic symbol. Now for the properties, to figure out the properties, once we find strontium, we figure out, okay, is it a metal or is it a non-metal? Or is it a metalloid? Because remember, metals are shiny solids that are malleable and conduct electricity. Non-metals are dry, brittle solids or gases at room temp, and they do not conduct electricity. And then metalloids is a combination of those two properties. So that's how we would figure out properties. And the last question asks what group number? Remember, group number are those vertical groups, right? 1A, 2A, 3A, etc. We can also give the common name if it's in one of the common groups, like the alkali metals, alkaline earth, halogens, noble gases, etc. All right, so looking at strontium, when I click the next slide, it's going to give the answer. So when you find strontium on the periodic table, if you can't find it, it's number 38, meaning it has 38 protons. So that makes it in group 2A. So since it's in group 2A, it does have a common name. Remember, group 2A is the alkaline earth metals. So since it's a metal, we know that its properties are going to be probably a shiny solid at room temp. It's going to be malleable, and it's going to be able to conduct electricity. So I think we've answered all the questions. So let's look at the answer. So they have written two atomic symbols here, strontium 87 and strontium 88. The reason they wrote both is because the average atomic mass is 87.62. So that means there's probably an isotope 87 and there's probably an isotope 88 in order to get that decimal. But you would have no way of knowing which atomic symbol is the correct one. And the properties, looks like we're right there, solid, metal, shiny, conducting electricity. It is in group 2A and the group name is alkaline earth metals. Very good.